In case you haven't noticed, I care a great deal about mechanistic problems and have been focusing almost all of my attention on teaching you how to understand mechanistic steps. And so a particular handout I want to draw your attention to is this Miller handout, where he walks through exactly how you're supposed to draw out mechanistic steps. And I really would like you to pay attention to all of this. But if there's one thing I would add to this list that he hasn't included, it is how to handle oxygens in mechanisms, and specifically when oxygens are allowed to be neutral or plus, and the way that this really reveals whether you understand acid-base chemistry well. So let me show you what I mean. So this is the problem from the bottom of that Miller handout we were just looking at. And one thing that I would add to Miller's list is always draw out any reagents over the arrow in good Lewis structure form. What I mean by that is it's useful to think of HCl not as three letters next to each other, but instead as H bond Cl. And that's because it makes it easier for you to start the mechanism the right way. This oxygen will attack that hydrogen. Why? Because this is a strong acid, and this oxygen is at least somewhat basic. The attack on this proton causes that chloride to leave. So after this equilibrium step, what I now have is a charged water, if you will. This is a oxygen that now has a plus charge on it. This oxygen can therefore leave so that it is now water and happy. There's a couple of subtleties I want to show here. First is, when the water leaves, this becomes a carbocation, which means not only that it is plus, but that it is trigonal planar. Therefore, I should draw it as flat with 120 degree bond angles. The water leaves as water, and that's okay. You can finish off the rest of the mechanism if you want, but now let me return to something right here at the beginning. We are under acidic conditions. How do you know that we're in acid? There's an acid present. You can never make an O- in acid, but you can make oxygen with a plus on it under acidic conditions. So this oxygen will pick up the proton, become plus charged. Once it is plus charged, it can leave as water. What you cannot do, what you can never do, is you can never have this leave just directly. Why not? Well, first of all, this is a terrible leaving group anyway. The oxygen just can't leave on its own to make the carbocation, because what would result there is O-. So OH- is a terrible leaving group. This will never happen ever. But the other reason for it is really this rule. You can never make an O- if you are under acidic conditions. As long as there's HCl present, you're allowed to have oxygen in its neutral form, oxygen in its plus form, oxygen in its neutral form. But you are never, ever, ever allowed to have oxygen in its minus form. This is not going to be a rule that we have illustrated at the moment, but if we are under basic conditions, you are not going to be making oxygens that are plus. Under acidic conditions, you can make oxygens that are plus or neutral. You can't make O-. Under basic conditions, you can make oxygens that are neutral or minus, but you can't make plus. That is a rule I want you to cement away. Here's another example of the same rule, except I'm not going to be under acidic conditions. I'm going to be under formally neutral conditions. But under neutral conditions, you can't make O-. O+ is a lot easier to make under neutral conditions. You can't make O-. So let's say I want you to draw out the mechanism for what happens here. My advice, as always, is to take any reagent that's over or under the arrow and draw it out in Lewis structure form. Yes, this is ethanol, same as that, but it's more useful to always draw this out in Lewis structure form. Well, in principle, you could look at this and say, wow, I have a nucleophile. Maybe it could go ahead and do an SN2 reaction like this. However, there are two problems with this idea. The first problem is that ethanol is a relatively crappy nucleophile and won't do that. The second is, this is a polar protic solvent, so SN2-like chemistry is a bad idea under these conditions. So, okay, most people usually recognize that this should be an SN1, so they draw that first arrow just fine, and now they have a cation and Cl- floating around. But at this stage, something funny happens. What people want to do is to use this chloride to deprotonate this hydrogen. But again, this is not something that is ever going to happen under neutral conditions. Under neutral conditions, you cannot make O-. Oxygens will remain neutral, or they will be plus, but they will not be minus. So don't do that. Instead, the process that's going to happen right now is that the ethanol that happens to be present here will go ahead and add. Once it has added, then you have an O+, and the O+ is capable of being deprotonated easily enough. But you can never make an O- under neutral conditions. So, okay, now that I've made the O+, again, these are all equilibrium steps because we can go back and forth, then in order to finish off the product, all you have to do is deprotonate, again, under acidic conditions or neutral conditions, the way this has to happen is via some O+ type chemistry. And that finishes off the mechanism. Your product is, of course, going to be the ethyl ether of isopropanol. One last bit that I want to point out, because I've been seeing this a lot, is if I have an example like this, where I'm saying isopropyl chloride will react under SN2-like conditions, you need to draw good Lewis structures. And so you really cannot solve this problem or get full credit for this problem unless you can generate the Lewis structure for N3-. So how do you generate a Lewis structure for N3-? Well, first things first, you count up the total number of electrons that are allowed to be there. So there are, in fact, 5 electrons per nitrogen atom, so that's 15 electrons plus another 16. This turns out to be a linear molecule. If you weren't aware of that, you should now be aware of it. 16 electrons is best done by drawing that out. Now you assign the formal charges, and that is the good Lewis structure. You may now use this in your reaction chemistry, and you should recognize that this is a good nucleophile because the nitrogen has a minus on both ends. It is small. Nitrogen is relatively nucleophilic. This is a minus. We're in a good SN2-like solvent. The mechanism is simply as drawn, and then the final product in this form, therein lies your answer. Of course, there would be inversion of stereochemistry if there was a stereocenter, but this is going to be an achiral molecule.